Okay, so today we're going to look at our final mechanism, and you may see it on a synthetic pathway as something like C2H4 goes to C2H5Cl. And this one is really, really important that you actually draw out for yourself and you see what it's going to look like. Because this product we have seen before from free radical substitution. But when we draw it like this, we can see that it is not substitution. It is addition, because I'm going from planar carbons here to tetrahedral carbons here. So this one is really, really important. And the difference between the alkene and the haloalkane is the fact that HCl has now been added. So this is an ionic addition mechanism, and our reagent in this case is hydrogen chloride. So we're going to get set up for how would we show the ionic mechanism for ethene and hydrogen chloride. So all of the same rules apply. I will just start by saying HCl, if you look at its electronegativity values, chlorine is naturally more electronegative, so it doesn't even need to be polarized. This is a polar bond in a polar molecule. So the double bond doesn't need to do anything. The approach will be like this because it is naturally polarized. The electrons would be down here, and the electrons in my double bond, it's dead easy now for them to go after this H+. They don't have to even do anything. They can just grab it, and the electrons here end up going to your chlorine. That brings us then to our next product. And remember now, the only thing that we say is we have heterolytic fission. The extra sentence that's not explicitly shown, heterolytic fission of HCl producing H+ and Cl-. Again, we've said if you're having issues with the diagram, then it's really important that you are writing all of the words. So it has to be one or the other, and obviously you've got to be right. You can put down both, unless you're saying contradictory things, it won't cancel. But this is the sentence that is not explicitly shown via diagram. We kind of skip the step. It's happening somewhere along this arrow. We don't actually see it. We just see the products. So the products of our first step will look like this. So you should now in your head be saying the label that's going to go onto this. So every time we write this, we write carbocation next to it. And we now have a chloride ion down here. So this has gotten the extra electron that was in the covalent bond, and it is now a full negative ion. And the electrons, the negative ion is going to go for the positive portion of your carbocation. So this then will bring us to our last diagram. And as you know, I go down before I go up. And the reason I'm doing that, again, just to remind you, while I'm going down, my arrows are all going down. When I get to the very bottom down here, my arrows now start to go up. And my chloride is always the last thing I draw for this particular diagram. So our product is now Cl. On the sides, we've said the halogens are big, so even though there's only one halogen in this molecule, we're going to put it on the side. And we also have to name this molecule. So chloroethane will do fine. I will always put the 1-chloro on it just to remind myself I have to put in numbers. So that is the mechanism for ionic addition. The last thing that we have to do is we have to talk about what would be the evidence for this ionic addition. So I'm going to erase over here for us. So we've said always the key is this carbocation, and when the chloride down here is going to add on, that is going to give us an expected product. So that's easy. That's expected because we had started with hydrogen chloride. It made a chloride ion that's going to go after this carbocation. So the evidence for this particular version of the mechanism would be if, so we'll still start with our carbocation. We'll draw it twice. So this is one of them, and this is going to be the second one. So our evidence for is if we had a bromide ion present. So a bromide ion would be a full Br minus. It's going to go after the positive portion of the carbocation, and it is going to make for us, doesn't matter where you put your bromine, I'm going to just put it onto this side because it was this side that was free. So it makes us bromoethane, and this is an unexpected product. So this is evidence that there must be a carbocation present, and the negative bromide has attached to it. Okay, so this is bromide because it is a full ion. The other piece of evidence might be if we had water present in our solution. And we've said before, stick it up here, water dissociates into H plus and OH minus. It's not going to let me do it. Into OH minus. And it is this OH minus now that is going to go after the positive portion of our carbocation. So that is now going to attach onto here. So again, just to remind you, this is a hydroxyl ion. We see it in bases. Obviously, OH in organic chemistry means something else. So this now is going to attach. And you should be shouting at the screen as to what it's making. So it has this OH group on it, 2 carbons. So it's got an eth beginning. It's an ethanol because it's now an alcohol, and again, this is unexpected. So your pieces of evidence are any negative ion other than chlorine for this mechanism, and these are the 2 examples that I would use, the bromide and the hydroxyl. So that ends the final mechanism. Well done.